We finished up talking about, well, we didn't finish up. We were talking about the language. The language being, well, so the representation is going to be this tree structure, but what values are we going to allow inside it? So if you're thinking to yourself, okay, a language, this is like a GP thing, we need to define the language. And no, you're wrong. It's not a GP thing. You need the same thing for every other, for like your GAs. You need to define what are the allowable values inside our chromosome. Here, what are the allowable values inside our chromosomes? That's all it is. It might feel a little bit more special because we're a little bit more explicit about what's included here. And usually with your GAs, you're gonna pick the set of values you allowed inside your chromosome and leave it alone. But with genetic programming, that might be something you tune. You might want to modify the values that you have in your chromosome, or that you have in your language, because maybe you really should have tan included, or maybe including E is a terrible idea. I don't know. So we set the operators. Some might be binary, some could be tertiary, and so on and so on. They could be anything. You can make them, they don't need to be operators, they can just be functions that take some arbitrary number of inputs. But, you know, for our purposes here, we could use these binary operators, some unary operators, and we need some operands. We'll call these terminals. These will be things at the bottom, like the leaves of the tree, that'll either have some constant value or might be some variable, right? So here is an example of what a tree could look like. We've got and Boolean operator, greater than Boolean operator, or binary Boolean operator, comparison operators. And on the bottom, I see a variable or a parameter, whatever you want to call it, a variable, a constant, variable, constant, variable, constant, right? So each record would go, okay, so what did it want? Say, size, shape, and shape. So the value of each record size, so if we're looking at this one, well, that's a 1, and it's a 1. So we would go, is 1 greater than that? Okay, well, that's false, and well, I don't even care, it's false. This classifier would say it's benign. Hey, so far so good. All right, that's how that would work. Now, one thing I'll point out here is if we're doing something like symbolic regression, which is a type of genetic programming we might want to do, where your goal is to just find some mathematical expression, some mathematical function to fit some data, like any form of regression analysis, you're only going to have one type, numbers. What I showed you before, there were operators that worked on numbers and Booleans. So that's like what they would call a typed genetic programming system, or a typed problem, where the types can change and matter within your S expressions. But when you're doing symbolic regression, you only have a single type. And weirdly, they call that untyped GP. It's typed, it's got one type, but it's untyped, meaning that the types, I don't need to be worried about the types because every operator and operand is ultimately going to be a number or evaluate to a number. So I don't need to worry too much about it. All right, typed and untyped. The mathematical expressions above only worked on numerical values. The breast cancer example had multiple different types. Addition to work on numbers, comparison operators, and some Boolean operators. Right? So the types could be either or. When using a language with only one type, we call it untyped, whatever. When using it with more than one type, we call it typed. All it does is, like, it adds some complexity to your algorithms, because when I do something like a crossover, I gotta make sure I pick, imagine I had two subtrees. Two trees, and there's another tree, I don't care what it is, but I pick this one. This subtree, I want to cross over with another subtree in the other chromosome, okay? But this subtree returns a Boolean. And Yeah, it's expecting a Boolean. If I were to exchange it with something that didn't return a Boolean, it returned a number and put it in here, we got a problem. So we need to be just extra careful how we're doing our genetic operators because it could break our trees. Does that make sense? Yeah? All right. Fortunately, fortunately, you're probably not gonna implement genetic programming from scratch. You're gonna use a GP system because there's a lot of extra overhead and crap you gotta take care of that I just don't wanna think about. So you just load up a genetic programming system and it manages all that for you. You just have to set it up correctly and then you hit run and you're good to go. Yeah, so yeah, when generating an expression that applies an operator to the wrong type, it would be a problem. For example, shape equals 4 plus 7. A Boolean plus 7? Doesn't really make sense. Yeah. When it's untyped, this doesn't matter. They're all going to be numbers, so it doesn't matter. Fortunately, this is all managed by your typical genetic programming system you're going to use. So typical GP system setup, we got to, like any other thing, we're going to have initialize the population, evaluation, selection, genetic operators, and some stopping criteria to keep doing it over and over and over again. That's it, just like a regular GA. So the key differences here come down to the representation. This is a course on evolutionary computation. This is not a course on genetic programming. So I'm not going to go into all the different details on how you might initialize a population and all that. I'm not going to talk about like grow or ramped half and half or all these different strategies to go how one would do it. That's too much into the weeds. But we generate an initial population randomly. There's a couple ways you could do it. It's evolutionary computation. Do whatever the hell you want. As long as it works, it works. Selection is still selection. Evaluation, well, you got to evaluate them somehow. Evaluation work depends on the problem, just like anything else. So, for example, for the breast cancer example, we'd have to say, okay, measure this classifier's accuracy on the data set, right? So take each record, throw it at this, was its classification right or wrong? Its fitness could be its accuracy. If you're doing symbolic regression, how close are you to what it should be, right? It depends on the problem. And crossover, yeah, here's what I was showing you. Typically with your, why is that 12 so big? And why is it, what? All right, weird. If I was doing crossover, like I was saying, typically your crossover is going to be like, you do a 1-point crossover, but you pick subtrees and you exchange them, right? So here, plus, minus, divide, if I replace it, yeah, we see that's there. And this will show up over there. There we go, right? There's an example of a crossover. Mutation, pick a subtree, replace it with a new subtree. This here it just so happened to replace this whole subtree with a single variable. Why? It could have been something else, doesn't matter. It's just an example. As a warning, typically, in genetic programming, typically, your mutation rates are kept really low. Very low. Very, 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 very low. There are exceptions, of course, and at the end of the day, you use whatever works the best. So if it's typically supposed to be low, but for whatever reason, when you cranked up mutation, you consistently got better results, good. But as a starting point, you're going to expect it to be low. And because it's so expected to be low, in spite of the fact that everything in evolutionary computation being a shit show and you just do whatever works, if you go and publish your work and you said you had a mutation rate of like 20%, reviewers are going to be like, why? That's weird. Because it's very peculiar. Now, bloat. Bloat is a problem that happens in genetic programming, and you're not really going to see in other forms of evolutionary computation. It's a big problem. With genetic programming, there's a phenomenon that as evolution goes on, your S expressions get bigger and bigger and bigger and bigger and bigger. Those trees grow over time. It's common that this happens. So it's actually not even particularly well understood. How do I word this? We all know bloat happens. We all kind of know why it happens, but it's not like well formalized or anything. But the trees tend to grow really big. And when this happens, they're growing bigger, but there's no real improvement with fitness. But the programs get bigger, like the trees get bigger and bigger and bigger over time. But the trees themselves aren't evaluating to anything that are better than smaller ones. So they get bigger and bigger and bigger. And this is problematic because obviously these trees take up more space. They take longer to evaluate. When they get bigger and bigger and bigger, they tend to overfit more. Usually your trees are going to overfit your problem more than not. Have I used the word overfit before? We talked about it before. Remember I drew that fancy artwork over there? Yeah. When trees get bigger, they're hard to interpret. One of the awesome benefits of genetic programming is when you're done, your best candidate solution is an S expression that you can look at and understand. It's visual. It's not like a neural network where when you're done and it gives you good results and you go like, oh, why is it doing what it's doing? And you go, good luck, figure it out. You don't know. It's just, why is it doing what it's doing? Because it's magic. With genetic programming, you can go, why? And you go look at a tree, like the ones I showed you, and you go like, oh, because it cared what the shape was. That's interesting. With your neural networks or a lot of other forms of like heavy-duty machine learning, you don't get such a thing. So genetic programming is great for interpretability, but when the trees get really big, they're definitely harder to interpret. And when the trees get bigger and bigger and bigger, your variation operators become less and less effective. And let's take a moment to talk about this. Why is this happening? Well, there's three core ideas here. One is replication accuracy theory. Parents, you gotta remember, let's think about the logic here. Parents are selected for having a good fitness, right? If I've got two parents selected and I want to do crossover, let's say. Those two parents were selected because they were likely relatively good, right? Children that are functionally similar to their parents will also be good, right? Larger trees are not as impacted. Let me take a step back. If the two parents did crossover and it produced an offspring that was functionally very different, odds are it's going to be worse than the parents. Okay? And they might go into the next generation, and then if it was a really bad fitness, it might die off and not get selected for, that child might not get selected for the next generation, so it dies off. If you have two parents and they apply genetic, like a crossover, and the child produces a similar result, functionally, like it acts functionally similar to the parents, chances are its fitness is going to be very similar to the parents, meaning they're also going to be relatively good, and it's probably going to get selected in the next, it might get selected again, right? Bigger trees are less impacted by the variation operators. If I have a small tree, on a small tree, and I'm doing, imagine the two trees here for a second. If I had two really small trees, these, I'm not saying these are large or small, I'm just showing you some trees here so you can ask yourself the question. Imagine I had two small trees. How many options do I have for selecting a subtree for crossover versus a tree that is really big? A lot less on smaller trees. And if I have two small trees, and I do crossover, it's going to wildly impact the parents. If I have a tree with, let's talk about an extreme case. If I have a tree with 3 nodes, root and 2 children, and another tree with 3 nodes, root and 2 children, and I select something for crossover, one of those children, they get switched. A third of those trees change, meaning that's going to have a big functional impact. If I have really big trees, a tree with a lot of nodes in it, the crossover is going to have a much smaller functional impact than it would on a smaller tree. Meaning, bigger trees are likely to be robust against genetic operators, meaning they're going to be functionally similar to their parents. And if the parents were selected because they were good, well, then the child's also going to be good. Smaller trees are more likely to be heavily impacted by the genetic operators, meaning they are going to be probably functionally different than the parents, which more often than not is a bad thing in terms of the fitness, meaning it won't live very long within the population. So the big trees it's this natural phenomenon, an evolutionary trait, if you will, to protect. The trees get bigger, they become more robust to variation, meaning that they're probably going to stay kind of good, so they won't die off. The smaller ones, they'll die off because they're more likely to be drastically different. Even if it could be better in the long run, they're going to be affected more by crossover, meaning they're more likely to die off, leaving only the big boys left. All right? All right. All right, thus large trees are more likely to be similar to the parent. Okay. Removal bias theory. Unless subtrees, useless subtrees with no meaningful function may exist within a tree. For example, look at this, right? This, again, I'm showing you an extreme case, but you can generalize from this. With larger trees, there is a chance that there's going to be useless chunks of trees. Bigger trees are going to be more likely to have things like this happening in it. This might not be a whole tree, it could be a subtree somewhere in it, right? But stuff like this is going to happen. And applying genetic operators to the useless subtrees has no functional impact at all. So once again, there is this selection pressure towards bigger trees. There's this implicit selection pressure towards bigger trees because it's less likely to be functionally different than the parents, which means they're less likely to get a little bit worse, which means they're more likely to persist. So another reason they're going to kick around a little longer. Now, in evolutionary computation, useless information, here's an interesting phenomenon. In EC, when I say useless information, it's really not necessarily useless over the course of evolution. There may have been parts of the subtree, a bunch of things could have happened. You could have had something very functionally important in a chromosome get crossed over into a useless part of a subtree that never gets expressed. All right? But because maybe those parents that had that important thing eventually die off, but this important thing ended up kind of existing in this useless part of the subtree, so it ends up being this vestigial pieces of information that could get crossed over out of the useless part back into a functionally important part and kind of re-arise, which is a really interesting phenomenon. Did that make sense? So it kind of temporarily gets put away in a box and is ignored, and then it pops back up one time, and then suddenly, oh, hey, it's back, right? Yay, good. So stuff like that can happen. Yeah, so it's neat. And then there is nature of programming space theory. The number, this is just a fact. How many ways I'm going to ask you a question that has a very precise answer. How many ways are there to write code to solve a problem? An infinite. Yeah. Are there more programs that are bigger that do the same thing than smaller ones? Of course. This evaluates to the number 4. You know what else evaluates to the number 4? You know what else does? You know what else does? A lot of things. But you know what else does that's really small? The number 4. The number 4 is 4. I could represent this, the number 4, in 1, 2, 3, 4, 5, 6, 7 nodes, or in a single node that is 4, or 2 nodes that's like 2 squared, or 3 nodes that's 2 plus 2, or 2 times 2. We could keep playing this game. And then I can have like plus 1, minus 1 down here, and it's all nonsense, right? It's just there are more bigger trees that mean the same thing as smaller trees, right? So that happens as well, yeah.
Not that it really matters, but is 2 squared 2 nodes or 3 nodes?
It would depend on how you encode it. If you could have like, you could have a square operator, or you could have a to the power of operator that needs 2.
Are they functionally different in the tree?
No,
Okay.
but it all depends on what you put in your language. That's a good question, right? So what we include in our language is entirely up to us. So here, I don't have a power of operator, but I could make the power of operator a binary operator, a base and a power, okay? Or I could make it a unary operator, but it'll only ever square something. And there might be a reason. If I'm like trying to do symbolic regression on some natural phenomenon, and I've got some reason to believe that something squared should be important, I might want to add square as an explicit operator in here just because I think it'll help the search. Another thing that'll happen is if I'm doing genetic programming or something, and I hit run, and after hitting run a bunch of times, like maybe a dozen times or so, I always notice this reoccurring like function pop up. Like x squared minus y squared is always just kind of appearing in the chromosomes at the end. So maybe what I'll do is I'll go and add that to my language to kind of like let the search start with what it's clearly discovered is already good and go from there. Although that does bias the search and you could end up in a local optimum. But these are all strategies people do, right? You just make it work. Yeah.
For numerical constants, is there like a good range to put in?
Depends on the problem. Usually, you start with small numbers. Like usually if I'm doing this, I'm going to start with like integers from like -10 to +10.
And fractions or just integers?
Well,
then you can just use divide, right?
so what I could do, what you'll notice in evolution, first of all, if you include like real floating point numbers, right, you're never going to find like, if the true underlying expression is like 4x plus 2.2, right? If you're using integers, you're obviously never going to find 2.2. But maybe it was like 4x plus 2. With integers, you find it. With floating point numbers, you're never gonna.
All your numbers
You're never gonna get a 2, right? Technically, you could, but the likelihood is very low. How many random integers are there between -10 and 10, inclusively? No, random integers. There's -10, -9, 20, right? 9, not 19.
Are we including -10?
Yeah, sure. Whatever. There's a finite number. How many floating point numbers? Well, it's still finite technically, but there's a hell of a lot more of them. I didn't say real numbers, I said floating point numbers because computers are computers, right? But how many real numbers are there then between -10 and positive? It's an infinite. So you're never gonna land on it, right? But what I'll usually do is I start with integers. And one thing nice about integers is you can end up with decimal values. Because what you can do is your search will take the constant 10 and divide it by 7, which will give you a decimal value, right? So even though the constant started as integers, they can produce decimal values by doing like rational numbers. So that's not all is lost with only dealing with integers. But if I'm doing if I'm doing like symbolic regression, and I'm going to start with constants between -10 and +10, because I think that's good. But I'm always noticing that at the end of the evolutionary search, I see like 10 times 10 times 10 popping up to form a constant. I'm going to go, okay, maybe my constants need to be a little bit bigger. Great questions, by the way. Those are great. Yeah, cool. Any questions about bloat or anything else now? All right. Now, symbolic regression with genetic programming. The purpose of this topic is to see what symbolic regression is. The genetic programming system used that I'm going to use is deep. Why? Because it's in Python, and to get it, you say like pip install deep, and you're good to go. There's a lot of other genetic programming systems out there that are a lot better than deep, to be honest, but deep is really easy to use. And much of the heavy lifting for implementing anything with GP is just done by deep. You don't need to deal with it. So you're good to go. So, symbolic regression. First of all, let's talk about regression analysis. You may have heard of this. Raise your hand if you're familiar-ish with regression analysis. A little bit. Regression is finding the relationships between dependent and independent variables given some observations. All right? A common and simple form of regression is linear regression. Find a linear relationship between some dependent and independent lines, or variables, right? So let's say I'm going and I'm observing. This is a very beautifully idealized scenario, by the way. Data is never this nice and clean, but let's pretend it is. I'm sitting there and I'm observing some phenomenon. And I'm noticing that, like, maybe this is, let me see. Well, what would be a good example of what I'm seeing? For some reason, I can't think of a good example of what this could be right now, but I've just got some observations, right? I'm sitting there, I'm outside, and I'm seeing like, oh, come on, what could this be? Someone think of a two-dimensional phenomenon I could be observing where it makes sense where the values are between -40 and, or -50 and +50 and -100 and, or -200 and, I don't know, 20 and +220. All right, whatever. I've got some data. Pardon?
Readings of a thermometer?
That's the best I could think of too. So I was like, temperature outside related to...
Temperature inside.
No, that really doesn't make any sense. It's so let's say the x-axis is temperature, all right, and the y-axis is happiness. Perfect. So I'm outside, or every day I show up and I go, okay, what's the temperature today? And this is over the course of a year, and maybe we live at, I don't know where we live, where the temperature range is -50 to +50 throughout the year, but maybe I'm traveling all over the globe, and I've got my amazing new, my tool for measuring people's happiness, right? So I go and I show up in Costa Rica and I go, okay, they're this happy. They're pretty happy. I go to Antigonish in the winter, I go like, they're not happy, right? I go to Winnipeg, oh, they're very unhappy, right? I'm doing that. And for whatever reason, my measuring tool, I know the temperature outside. I can measure that, and the temperature is pretty clear, right? But I've got this mechanism for measuring people's happiness, right? And I've got a hypothesis. I go, I think there is a nice relationship between temperature outside and arbitrary units of happiness. All right? So I want to say can I find a nice clean function, mathematical expression, that if you tell me the temperature, I can tell you how happy those people are that day. Okay? That's what I want in this ridiculous hypothetical situation. So I want to be able to take this data and generalize it such that if I know tomorrow it's supposed to be 20 degrees out, I'm going to be like, everyone's going to be like 80 units happy. Okay? I want to know that function. So what is the relationship exactly between temperature and happiness? Some function of the temperature will tell me the happiness. Okay? So far so good? I realize I'm describing a 2D plot, so it's like we're back in grade 9, but there we go. Now, when you look at this data, an experienced person would look at this and go, that looks pretty linear. Meaning, I can like draw a straight line and it's probably going to do the trick. And because of that, I'm going to say I want to do linear regression. So what do I say? Observations of some phenomenon plotted in 2 dimensions, dependent variables plotted along the y-axis, independent is the x-axis. I have that right? Independent is the y-axis. I think I have that backward. Oh, I'll check that later. My brain's not firing correctly. From a quick glance, the data is clearly some linear relationship, right? So given the above observation, the goal is to draw a line of best fit. And the line's probably going to look a lot like y equals mx plus b, right? I swear to God, this isn't grade 9, but it's probably going to look like that, okay? Now, the question I have is, what is the best line? I could eyeball it here, right? I'm going to grab like a ruler and go, okay, you know, it's pretty good. What's its slope? You know, calculate rise over run. What's the y-intercept? Well, I can't quite see, but I can probably guess where it would be with the line, you know. So what is that equation? And you know, when I eyeball it, how good is it gonna be, right? This data, it's hard to tell from here, but you can, it's not actually perfectly linear. There is some variation in the data, and you can kind of see how like the lines, like there's some ups and downs. It's just the scale is so big that you can't really see. So it's not perfectly linear. The question I have is, what is the best line? There exists a line such that all points are minimally far away from that line. Okay? That it does exist. So how do we find it? Well, we would do linear regression. The mathematics of how linear regression works is outside the scope of this course. It's actually relatively straightforward if you understand like first year calculus and first year algebra, but we're not going to get into it. Fortunately, there's a really easy way to do it. You load up scikit-learn and you say, do my linear regression for me, right? You do that.
Is there a reason that the scale changed between the 2 graphs?
It's a good question. Probably because I did it.
It's the exact same size as the y-axis.
It's probably because that's a good observation, and I want you to listen to me right now. I want you to go to the GitHub repo and post an issue saying there is an inconsistency with the scale because I got to fix that. That shouldn't have been there. The reason it's probably different is because I saw this and was like, that's too big, and then I changed it here and forgot to change it in the other one. So there, I loaded up scikit-learn, and I did scikit-learn.linearmodel.linear regression. I gave it the data, I said fit, it gave me my line. And I drew the line. That is the line of best fit on top of it. And what does that line look like? Well, that line is 0.999885x plus 0.997937. And it has an r-squared value of 0.9999. Basically, an r-squared of 1 is perfect, right? A higher r-squared is better for your linear regression. The reason this isn't perfect is the data was a little noisy. We weren't really going to be able to get a perfect line. This right here, if you're doing any observations of real data and you get an R-squared value of 0.999999885, you've hit the jackpot. You found it. Okay, you're right. So that is my line there. Now, you'll see, I didn't call it y equals mx plus b. When doing regression, often you'll see like, well, y hat equals that. Y is what you really observed. Y hat is your prediction of y, just as a heads up. So there's our model. Y hat denotes that it's not y, but it's a prediction estimator of y. R squared is that. That's the measure of goodness in your typical linear regression. The closer to 1, the better the fit, right? Cool. Any questions so far? Now, if you were to say, all right, regression analysis, it's great. And now I'm measuring, what could this one be? Now I want to know the relationship between temperature outside and the amount of, what could this be a measurement of? X is the temperature outside. What is Y here?
Strong emotions that someone has, either happy or sad.
So,
It's hard to think of real world examples of what it means.
It could be like temperature outside and angerness levels, right? Even though people are, I didn't know this, but apparently when it's 0 degrees, people are not angry. Now, happy and angry don't need to be mutually exclusive, let's say, right? So they can be, we saw previously, our discovery was that as it gets hotter outside, people get happier, but they can be happy and angry at the same time, apparently. Go with me on this, all right? Just pretend this is the case. So when it's around 0 degrees, people are, they're not too angry. No, let's not say anger. Let's say powerfulness of their emotion. Motion intensity.
I got one that might not
Okay,
actually
let's
be
see it.
arbitrary. Power consumption, either like lots of heat or lots of AC.
Okay, fine. Yeah, there we go. Cool. Even though this should probably be shifted a little bit closer,
Yeah.
like this way. But let's say this is the way it is. All right, that one, I like this one. Power consumption and temperature. It gets hotter, people are pumping their AC. It gets colder, people are pumping their heaters. That's a much better one. Thank you. Yes, very good. So there we go. And I say, great, I just did regression analysis because I wanted to be able to tell you, to come up with a function that you tell me where, like what temperature it is, and I tell you how happy, or sorry, the power consumption, right? To tell you the power consumption. That's the goal. Now you could say, why would I want a function when I can just look at the plot and be like, okay, -20 is going to be like, they're 500 units of power, right? Why would I even need a function if I could just look at the plot? You got to the plot and the function are equivalent, right? It's just a plot is visually, the function is mathematically describing the same, but they're the same thing. So let's just come up with the function that would describe this plot, right? So that's what I want. And it's a little noisy, it's not perfect. You can see there's a little bit of noise in here. But this is nice clean data. So let's try some regression analysis. And I do, and I get this. That is the line of best fit for my regression analysis here. This is the line. I could not draw a better line than this. Let me check something. Yeah. I cannot draw a better line that fits this data better. The issue is, well, first of all, you look at this. Is that a good line? Does that line fit the data very well? No. But I'm saying, no, it's the best straight line that I can draw. The issue here is I was requiring my thing to look like y equals mx plus b. This requires nonlinear regression. Linear regression is nice and easy and great to use. Nonlinear regression, you're screwed. You can do it, but it requires a lot of assumptions. It requires you to look at the data. Now, in this particular one, I'm going to say it's probably like a quadratic thing, right? There's probably like a squared in there, right? Probably. I don't know. Maybe if I were to keep going, it wouldn't be, but often you got to remember too, often when fitting data with regression analysis, you do have bounded like ranges and domains, meaning that like if your function fits really well between -50 and +50, but if you were to know what it was like at +100 and it was way off out at that end, I would go, well, I don't give a shit. I've got a great predictor between -50 and +50. Because it's usually not that much hotter outside than that, so it's good enough. Anyways, I would need nonlinear regression. And nonlinear regression requires a lot of guesswork. All right, it's still possible to find how models, but it requires several assumptions and a lot of guesswork. It requires a lot of guesswork, a lot of assumptions. I would need to do linear regression of nonlinear basis functions. I'd need to know what those nonlinear basis functions are. There's a lot of stuff I would have to do, right? And there's no guarantee it's going to work. But I got some good news for you. This is where symbolic regression pops up. If I throw symbolic regression at this data, here's what I got. It's pretty damn good, doesn't it? Symbolic regression is done with genetic programming. Symbolic regression does regression analysis. It tries to find a function to fit this data, but you really don't need to make very many assumptions about your data. You don't need to do a lot of guesswork. The most guesswork you have to do is, what do you want to include in the language, but you can tinker with that all you want. Doesn't matter. If I gave you this model or that model being the line, which one do you prefer? Obviously this one, obviously. This one, after fitting it, my model came up as 1.100511x squared minus 4.439578. It had a mean squared error of 0.162087. Now, when doing symbolic regression, you're typically not looking for an R squared value. You're looking for something like a mean squared error, which is basically how far away is each data point from where I predict it should be squared, averaged, okay, mean squared error. Now the reason we like mean squared error, by the way, oh yeah, well, I'll come back to this in a second. The reason we like mean squared error, you could say, why don't you just like mean absolute error? Why are you squaring the error, right? Both of which, smaller is better, so why are you squaring the error? The reason we square the error, the reason mean squared error is a great metric is because it punishes those that are more wrong more, right? If I was off by 3, I'm off by 3. And if on another point I'm off by 4, I'm off by 4. I have a total error of 3 plus 4. And the 4 got 4 units of error, and the 3 got 3 units of error. But when I'm doing squared error, my error is 9 and 16. Even though 4 was only 1 unit worse than 3, its punishment is way higher once you start squaring it. It's a great way to kind of like get your function to get closer and closer faster. It's nice, it's good. Now, one thing I will note, so yeah, mean squared error, it's not R squared. Here, 0 is better, FYI. In reality, symbolic regression is wild. So when I hit run, I didn't get 1.100511x squared minus 4.439578. I didn't get that. What I got was add protected divide of the multiplication of x by x divided by 9.949161 multiplied by x squared. Okay, what's going on? Okay, so what's happening here? Let's see. Let's simplify. If I draw over here, you're going to be able to see over there? So let's draw this out because this is actually an inline encoding of an S expression. So we have add. Let's try this one. I'll have to go through these markers. That looks pretty good. We have add, and then so we have add, so this is the multiplication, that, and that's the divide.
Then it's protected divide.
Well, hold on. So we have add, you know what, I can go this way. Protected divide, that's just divide. And we're dividing a multiplication of x and x. And over here, we're doing it with 9.949, 9.949, I'm not going to write the rest. And then we're adding that with the multiplication of x by x. And then minus 4.439. That's what genetic programming gave me. But let's simplify this a little bit. So we have this is x squared. So this is now x squared divided by, right, I'm just going to draw it like that, right? And then I add to it x squared, okay, x squared plus that, plus minus, well, okay, so that's the equivalent of minus, this is, go with me, minus 4.439. I may have done this wrong even. So x squared plus x squared divided by that. Did I do this wrong? I feel like I simplified this wrong.
No, it's right.
Is that, yeah? Okay. Right, okay. Yeah. So, now I have x squared plus x squared divided by 9.949 minus 4.439. All right, so we can clearly see the 9. So now, what is x squared divided by, how does this work?
I'm guessing it's 0.100511.
I'm guessing that's what it comes out to as well. So we see 1x squared plus what I'm with you, 0.100511x squared minus 4.439 and 1 plus that, and huzzah, right? Genetic programming won't ever give you something nice and clean. You always have to play a little bit of this game after, which is always the fun of it, right? So, anyways, that's all good prep for deep. Did you submit the issue?
Yep.
Nice. I probably won't fix it this year, but I'm glad it's there because otherwise it gets forgotten. Any last questions? Yes.
I had a couple questions on this. The first one is so there are like 100 sample data things, so would it be better to approach it from the perspective where your algorithm just does one of them tries to do well, or tackles all 100 of them?
All of them. You want to do each one of those rows is 1 point.
No, but I mean, there were...
Oh, I gave you like 20.
There were 100 sets of rows. So there were 100 different functions.
No. There's only each file contains one each row is one observation of a function.
Files.
There were 100 files? There should be 20 files, yeah. So each of those will have a different function used to generate it. So here's what I did, is I went into Python, I wrote in a function, and I said, give me random values between negative something and positive something, and give me the output of the function, add a little bit of random noise to it because I'm sadistic, and then your job is to tell me which function I used to generate that. And I did that for each of those files.
So they're algorithm probably only be doing that for like one file?
One file at a time. Yeah, the functions are entirely independent from one another. Yeah. Do you had other questions about it?
The other one was just wondering if we could section
When does it due?
Monday.
It's due this Monday. So at this point, I don't care. I can give you the extension, but I mean, now it's cutting into your project and everything else, right? So, I mean, I could do that if you want. It doesn't matter to me. I've seen people go like, okay, but then don't come whining when you're like, we have so many things to do at the end of the semester. All right, yeah. All right, I'll do it. If I forget to do it, remind me next time, but I'll try to remember to go do it right now.